The world is filled with scientific anomalies, many of which occurring in the field of optics. When we think of light, we think of a ray, probably because light is made out of particles. So logically speaking, light should behave like a particle. But does it really? Is light a wave or a particle? Well, actually, it's neither one, it's both. The fact is that the true nature of light defies mental picturing, because it's not quite like anything we can lay our hands on. Under certain circumstances, light does indeed behave like a wave. However, under other circumstances, light behaves in a way that only particles can. This is called a wave-particle duality. A particle is a minute portion of matter, and is described as the smallest unit in a substance. They can travel, reflect, refract, and interfere. When they travel, they go straight and do not spread out. Waves, on the other hand, act in many different ways, depending on their length, frequency, and surroundings. They may produce reflections, refractions, diffraction, and interference. As a wave continues to move, it spreads and expands to cover a larger area. Basically, when light is exhibiting a wave-particle duality, its particles are guided by a wave function or pilot wave, which, depending on its size, determines the particle's speed, angle, and destination. But how and why is this possible? Well, there are 3 laws that particles must follow before exhibiting wave-particle duality. Law 1. The wave, particle, and medium must have the same constitution. Law 2. When a particle is moving, it must become a wave. Law 3. During a wave-particle duality, particles must be in one of 3 states: particle state, no motion; wave state, in motion; or transformation state, in between motion. Because of these 3 laws, we are able to understand the complex nature of a wave-particle duality. At first, scientists were reluctant to accept or even identify the dual nature of light due to its strange concept and irregularity with mathematics. Yet in 1905, Albert Einstein changed the image of light in the human mind by simply embracing its true nature. One of his experiments played an extremely crucial role to understand a wave-particle duality in light. He discovered that when light is sprayed on metal, a spray of electrons detaches. Magic? Not really, just simply an experiment that displays light's dual nature. Conducting this experiment several times, he finally proposed that light delivers its energy in chunks, consisting of photons, and later named it the photoelectric effect. Then in 1927, French physicist Louis de Broglie hypothesized that if light photons can act as both a wave and a particle, perhaps a regular particle, such as an electron, could also exhibit the properties of a wave. He stated that the formula for identifying the size of a particle's pilot wave should not only apply to the photons of light, but to any other particle. This formula determined the variables affecting the location of a particle during a wave-particle duality and resulted in the expansion of the theory from light to matter. By now, many of you must be wondering, what's the big idea? Sure, particles have a wave-particle duality, but how does it affect us? Well, the wave-particle duality theory has not only had a large impact on the scientific community, it also has an impact on our everyday lives. One little device courtesy of this theory is called a photoresistor, aka a photocell. Photoresistors exhibit a photoconductivity where an object becomes more conductive by absorbing electromagnetic radiation, most often found in light. Photocells are also the basic unit of solar panels, which convert sunlight into electricity. Large solar panels are used to power space stations and satellites, and these panels are an eco-friendly way to operate billboards and safety lights in remote areas far from power lines. One example exhibits the relation of the photoelectric effects in the category of space exploration. Exposure to sunlight will cause spacecraft to develop an electric charge, which could result in damages to electrical components. This could lead to major problems in space shuttles, and end a repeat of the Apollo 13 tragedy. However, scientists were able to apply their knowledge of the photoelectric effect and protect satellites and spaceships with an effective guard against the harsh powers of the sun. In other words, without our knowledge of the wave-particle duality theory, man would have never landed on the moon, and life would be pretty dull without everyone's afternoon snack of crackers and moon cheese.